I'll just do the derivation quickly. So the kind of elementary that we need to take is well known to us. Like the moment you see a spherical object, you know how to take element. So elementary must be along the slant, right?
Yes.
Now this is the part which one should learn. The derivation is again easy, but remembering that what should be taken is important, and what kind of elementary every time we see while deriving something is important. And then you see there's a pattern. I mean, we don't have much of variation in creating the elementary. Okay, it is like it's well defined, and just we need to follow the same routine process. So technically, it's a routine process. So this is your elementary cylinder actually, because it's a hollow, and it will act as a ring for the point O. So O is the point on the axis of this ring, and this ring will have a charge dq, which we can calculate using sigma dA. And just for the sake of completeness, this is theta, this is d theta.
Yes.
And okay, so now this is the charge. So we have a charge here, and the radius of this shell is capital R. But the ring that we have captured here, the ring will have the radius is small r, which you can of course write in terms of capital R, which we have been doing again and again. So this R is R cos theta,
Cos
right?
theta.
And then we know how to find the area vector. So the area magnitude. So area will be how much?
2 pi
The
r cos
2 pi
r
r
cos theta.
cos theta into the slant length, which is r d theta.
Yes.
Yes, sir.
So once we have this value, you can write the dq equals to sigma dA. But anyway, the question is, if it is a ring, the formula of the ring will act as the elementary. So we are supposed to use the ring formula to access the elementary value. So we can write the dE, the electric field that the ring will create at O. The formula is well known to us. And what is the
A
formula?
dq x upon
A dq x upon x square plus r square, which is the slant length only, right?
Yeah.
That is slant length. Power 3/2, which means it's r cube actually.
Yeah, and x will be r sin theta.
And x will be r sin theta. Excellent. So the next step is this will be K and dq we run now is sigma into dA, which is 2 pi r square cos theta d theta. X itself is r sin theta upon r cube. Now you can see clearly that all r will cancel out. So what is this is really interesting. So what we are
Sine
left
2
with
theta.
is yeah, this is like K sigma pi into sine 2 theta d theta. And now you are just supposed to integrate. Now the question is, what will be the limit of integration? So we are only supposed to capture from bottom to the top. So theta 0 will give you the bottom and theta 90 will give you the top, and that's it. So we have to capture only from 0 to 90. And this gives the net plateau. Sine 2 theta, what is the time period of, what is the period of sine 2 theta? It's pi. Okay. So pi by 2 is the first part, like the positive part, and the integration we know is always 1, right? So integration will give you some 1, so you can add this as, or if you want, you can explain, you can add minus cos 2 theta by 2 and then limit, and you will get the same answer. So having this answer, we can add 1 by 4 pi epsilon naught into sigma into pi, and this turns out to be sigma upon 4 epsilon naught. So this is the answer. Okay. So this is the electric field value at the O. And what is also interesting that you come to know later on through some rigorous proof, that the direction of electric field at the base, so we got the value, and the value is sigma by 4 epsilon naught, and the direction will be like this, vertically onward, right? Because every ring which you will cut will create the field along the axis, isn't it?
Yes.
Now, what is also fascinating to know that no matter which point you choose on the base, the net field is always downward. Although value will change, but it is interesting to know that the field is always downward everywhere at the bottom. That's a very fascinating result, which as of now you can just remember. When the right time will come, I'll prove it. Okay. So this is the electric field due to the hemispherical uniformly charged shell, and this can be derived using the ring formula which we have already used. So we have taken the ring formula for two types of derivation. One was the disk, and now it is a hemispherical shell. Okay. Now, because you know the formula for the hemispherical shell, you can actually derive the formula for the solid hemisphere as well. Now, that's very interesting to find the, uh, but I don't think it will. Okay. Yeah, it will give you the answer. Interestingly, let me just check if it is meaningful answer or not. So let's say we have a solid hemisphere. Let's say we have a solid hemisphere, And we know the answer for the, and rho is the volume charge density. So in this case, rho is the volume charge density. So definitely we can attach dq by d volume, and if the density is uniform for the uniform distribution, we can directly write the rho equals to u by v. But here we have to express the answer in terms of rho itself, so no need to worry much. Now, what kind of elementary we need to take here? So, of course, whatever answer we know, we can take two types of elementary here. One is a disk. Why? Because we know the formula of disk. And we can also take the shell because we know the formula of shell also. So we can use the hemispherical shell to derive the answer.
Yes.
So again, I'm saying there are two options possible here.
But this formula is pretty big, so shell will be easier.
Yeah, the shell is definitely going to be much easier. So the elementary that we have cut here will have some radius, let's say small r, and some thickness we have to assume, and we know the thickness must be dr, right?
Yes.
So the sigma and the rho will have some relation because sigma is the way in which we express the answer. So we can see the dE at O will be sigma by 4 epsilon naught. That was the answer, right? Now, how to define sigma for a shell? What is sigma? So we have to equate the charge in two scenarios. So charge in that thin shell will be how much? Density into volume of the shell. And the
Yes.
volume of shell will be how much? The surface area, which is 2 pi r square, half of the full sphere. So rho into area into thickness is the charge. So this is the charge that we can express in terms of rho. In terms of sigma, the charge we can write as sigma into area only. So there are two ways in which you can express the answer. One in terms of sigma, other in terms of the equivalent rho. And if you compare these two, you can clearly see the rho dr is the sigma. Okay. So sigma is how much? Rho dr. Understood?
Yes.
And that's very simple. Like always remember that the rho into thickness is the sigma. Always. So now we can say dE not equals to rho dr upon 4 epsilon naught. This is the easiest question that we can solve. So the electric field turns out to how much? Rho capital R by 4 epsilon naught. So that is the electric field. It is clear?
Yes, sir.
Just so due to solid hemisphere with uniform charge density rho. So now this is the answer for the hemispherical. We have derived the formula for, I think, semi-circular cylinder and all those things, right? Yeah, in the starting class. So we have done with all formulas, ring, disc, hemisphere.
Also we do.
Pardon?
Arc of
Yeah,
symmetry.
arc. Yeah, of course. Arc. So I think now we can go to the next concept, because there are some derivation which we would like to do or finish after the Gauss law, so that will be easier for all of us. Okay. Okay. So one more thing, okay, I just forgot to discuss is the disk formula. So in case of disk, so physically, if we have a disk, can we have a disk without thickness? Is it possible to have disk without thickness? Certainly not. So physically, everything, if we try to create, it will have three dimensions, all dimensions. The only thing is we try to keep it as thin as possible. So we uh, see a disk is, of course, a thin cylinder, basically. So this is also a way of thinking that a disk represents a thin cylinder, and sigma is some sort of a representation, the way you want to express the distribution. But in reality, every distribution begins with rho, and every other representation, which is only meant for the convenience. Okay. So what I'm trying to show, a small, or you can say thin disk, and however thin it may have, I mean, it will have some thickness. Let's call this as T. And if you think area as radius as capital R, the area of the disk will be how much? Pi r square. So what will be the volume of the entire disk? So volume you can write as
Pi r square.
pi r square T, right?
T.
So I'm just writing AT, area surface area into thickness. That's easy way of writing. So the charge in the disk, you can say any charge, you can name Q charge. Let's say the charge is Q. The charge in the disk will be how much? Volume density into volume. Rho represents the volume charge density, which means charge present in unit volume. So how much charge is present in the V volume? So we can simply add rho into V. Okay. So when you try to express in terms of sigma, then what sigma represents? So you try to show like this, the charge is here, but the charge is in reality, charge is present everywhere throughout the thickness. So the other way of writing the charge will be sigma into visible area, the area which you face. So what area you face? A only. So the same charge in the disk can be expressed either sigma into A or density into volume. And again, that clearly shows the relation which I was talking about. So the sigma is always equals to density into thickness. And in the previous question, thickness was dr. So we write rho dr. Can you see that? Rho dear. Tell me guys. Now is it making sense to you? Why we are
Yes.
written like this?
Yes, sir.
So always remember that sigma is not real, rho is real. So lambda or sigma are two subtle representation, and these representation are meant for some sort of convenience. It's easy to write. Okay. So now the formula which you derive. So due to disk at any axial position, x distance away, you derive the formula, and the formula was how much? Anyone who remembers the formula? E equals to, the answer was in terms of sigma. Can you tell me what was it?
Sigma by 2 epsilon naught.
Sigma by 2 epsilon naught.
1 minus x
1
upon
minus x upon.
root of x square plus r square.
Right. So this was the formula. Now, in this formula, what x represents? Because we need to discuss what is x.
Distance from the center of the ring.
Yeah, x is the distance from the center of the surface actually, not the center of the thickness. That's very interesting that we never go inside. We only remain at surface. So let me mention this explicitly. X is measured from the center of surface, not the physical center. Now, you may ask why this is so important to mention. So, why it is important to mention that if x is equal to 0, if you put x equal to 0, what do you expect the answer? 0 or non-zero?
Non-zero.
So the answer turns out to be sigma by 2 epsilon naught. And this is not equal to 0, but in reality, if you go at physical center, it's like you have a wafer and you slice into two small wafers. Or maybe these are two sticky notes which are like stuck together and you think it's a one. But with some careful observation, you can see or realize it's two, you can trying to tear apart. So if you go exactly at the center, what do you expect? The field should be 0 or non-zero.
0.
At physical center, it cannot be non-zero. It must be 0.
Yes.
Because the left disk and the right disk will cancel each other field. And you are left with 0 answer. Isn't it?
Yes.
Anybody getting this idea what I'm discussing here? So
Yeah.
x is not something which we measure from the center of the physical center. X is something that we measure from the center of the surface of the disk on either side. It doesn't matter which side you choose. So there is a difference between the physical center and the center of the surface, and this confusion is very much prevailing, and therefore I just wanted to explain explicitly. So now if you put x equals to 0, you get some answer because you're trying to find the electric field just outside the surface. So what is the meaning of x equals to 0? Finding the field just outside the surface. And what is the answer? Sigma upon 2 epsilon naught. So now this answer is true for any surface with given sigma. That every surface will create a field of sigma by 2 epsilon naught. Okay, I hope this is clear.
Yes.
Yes.
So we'll take one interesting scenario. What if the disk becomes infinite. So infinite disk means the radius tending to infinity, and the infinite disk is also called the infinite sheet. And because the charge is prevailing in the volume of the sheet, so we call it non-conducting sheet. So again, if you make R really infinite or big enough compared to the point which we are talking about, the formula for E will become how much? If you make R infinite.
Sigma by 2 absolute.
Now this is not a miracle. This is really interesting. I mean, scenario. You can see at x equals to 0, the answer is also same as we assume if the disk is infinite, which is something very meaningful. Why? Because if you're really close to the center of the disk, imagine an observer which is standing next to the center. For that observer, the disk will appear infinite. So when you move very close to any surface, you will feel that the surface is infinitely large. Do you realize this?
Yes.
Yes, sir.
So if you go very close to the surface will appear infinitely large. Clear? So both
Yes.
scenarios are similar, or you can say equivalent. So for any infinite sheet, the answer remains sigma by 2 epsilon. But how the sigma is defined? The sigma is defined as rho into thickness. And this leads to the next concept. So there is a very popular concept called the flat earth concept, right? Imagine if we are having something really flat and large. So it's a really big planet. Okay, so now before I discuss this, I'll discuss something called the thick disk. So what is thick disk? Now the thickness will be clearly mentioned to you. Let me show you a disk only by the side, only by the looking right now is the only thickness. So I assume this is thickness. So I'm just trying to zoom the thickness for the better understanding. You may call this a side view of disk. Okay. And let's say thickness is T again. So if you draw any central line, and if you move from the central line by some value, let's call it x, and then you can choose a point P here. So I'm assuming this is thick disk, but infinitely large. It's infinite disk. And what you're looking at is the side view. Okay. So actually the disk is like this. You can understand. Now the question is, what is the electric field at the point P? Can we find the electric field at point P? Can we find the electric field at point P? The answer is yes. We can find the answer at point P very easily. How? So basically, the point P is the sandwich between the two separate disks. So you can think this as a sandwich of two disks, and the first disk having thickness how much? So what is the thickness of the first disk?
T by 2 minus
P by 2
T by 2 plus x.
plus 6. Similarly, what is the thickness of the second disk?
T by 2 minus.
By 2 minus x.
So you can realize that the point P is in front of these two separate disks. So what we need to understand that sigma depends on thickness. So it is like the point P is in between two separate infinite sheet of varying sigma or different sigma. Not varying, of different sigma. So what is the sigma of the first? So sigma 1 will be how much? So can we write sigma 1 as, yeah, you can guess.
2 pi r T by 2 plus x.
What is the sigma formula? Sigma is volume charge density is given rho.
Oh, that.
So sigma will be how much?
Rho into thickness.
So
Which
what
is
I will add thickness?
T by 2 plus x.
Very good. So sigma 1 is rho into T by 2 plus 6. So similarly, what is sigma 2?
Rho into T by 2 minus x.
So definitely the more the thickness, can we say more the sigma? So the E1 will be right. So the first sheet will create the field towards the right because the point P lies at the surface of the infinite disk, isn't it?
Yes.
And what is the formula for the infinite disk? Tell me. What is the formula for the
Sigma
infinite disk?
upon 2
Sigma
epsilon.
upon 2 epsilon. But E2 will create field like left. So the sheet on the right will create the field towards left because point P is on the left of the sheet, isn't it?
Yes.
So now we are done. So what is the net field now? Because we're looking for the net field, right? So can we say E1 minus E2?
Yeah.
So what is E1 minus E2? Is sigma 1 minus sigma 2 upon 2 epsilon naught.
Yes.
And if you take a difference of these two, what will you get?
Rho x upon epsilon.
2 rho x upon 2 epsilon, which is rho x.
Rho x upon.
Now this is the real answer. So this is the inside the sheet. So from center, if you move x away, the inside the sheet, the field formula is rho x by epsilon naught. So by the time you reach at the surface, how much x will change? From center to surface, x will go from where to where?
So what did you ask?
So if you go from center to surface, what will how much x will vary?
T by 2.
P by 2. So at surface, the formula will be the electric field will be how much? We need to put x equals to
T by 2.
P by 2. So once you put T by 2, the answer will be rho T by 2 optional.
Yes.
But rho T represents the net sigma of the entire sheet, isn't it?
Yeah.
Yeah.
And you can see the answer becomes again
Oh,
sigma
that's
by
why it is.
sigma by 2 optional.
Yeah.
So now this will help you in realizing that the x in the disk formula is something which we measure from the surface, not from the center, not from the physical center. Okay. So now is this clear, guys? What is the true meaning of x in the disk formula?
Yeah.
Yes, sir.
So what this x represents is quite different from what x I'm taking here. So you should not get confused between the two. Both are distinct and different things. And this formula is only true as long as you are within the volume. Okay. So the domain of x will be minus t by 2 to plus t by 2. Let's say. So you can go on either side, and so when you move left, don't put a minus sign, put the value to it, because what we need is the thickness, and negative cannot be thickness, but it's just a domain. Okay. Or better, I can write this as I think minus t by 2 is confusing. The value of x will change from 0 to t by 2. That's it. Now every formula that we derive in electrostatic will have the equivalent in the gravitation as well. So imagine we have a thick planet, in say a circular planet. Okay. So I'm taking thickness as T. Okay. So now let's say you think of it, digging a hole from center to the bottom. So this is the ambitious project of Elon Musk. And you're trying to dig a hole from the pole to the bottom, okay, pole to pole. So now again, if I say the rho as the volume mass density, and if I assume the radius to be really infinite, it's a of course a planet with a very big radius. So for all for all practical purpose, we can assume R to be infinite, or R to be, even if it is much bigger than thickness, it is infinite. Okay. So now from center, if I move y distance ahead, let me do it separately. Side view. It's the same question. If I move, or let's say if you make a, if you go from surface at a depth d, what will be the value of gravitational field intensity? So question is, find gravitational field intensity, which is equivalent as acceleration due to gravity, because both are same. So find gravitational field intensity at a depth d from surface. So what will be the answer, guys? So we can write G is nothing but similar to the electric field that you got. So you can find the answer of electric field, and what is the conversion factor, if you remember? 1 by epsilon naught we write as 4 pi g, or 1 by 4 pi epsilon naught we write as only g. The electrostatic K is equivalent of a gravitational G, and therefore if you do the reverse, you can get 1 by epsilon naught as 4 pi g, and this conversion factor you can use to relate to different chapters. It's called so this is the analog relation between the gravitation and electrostatics.
So here it will be rho t upon 8 pi g. Right?
Here it will be how much? Rho by,
Upon 8 pi g.
so how we usually write rho x upon epsilon, right? From center.
Yes.
So d from the surface, how far from center?
T by 2 minus 2.
The answer is rho x. That's it.
Yeah. Okay.
But we cannot write this now.
Yes.
So we cannot write 1 by epsilon naught here.
Yeah.
So answer turns out to be really nice. The g value at a depth d is equals to 4 pi rho g into t by 2 minus d. So questions like this can also be asked in the examination. Just be ready that you can always relate the Gauss. I mean, this is okay. Sorry, this is the Gauss law. In general, we use this, but you can always relate the electrostatics and gravitation with some tweak of the constant values. The interpretation will change, but the formula will have quite a good similarity. I hope this is clear.
Yes.
So now again, this is the question from S.C. Verma in Gauss law you have to solve. This is the maybe third last or fourth last question in S.C. Verma Gauss law chapter. Okay. Not this question, this question. This is the question from S.C. Verma. So after learning the electric field, so various shape, size, and various line charge or various arc and their combination. We've done almost all type of question. I think all variety we have discussed. So now we can go to the next concept, that's called the electric field lines, or it is also called electric lines of force. So now this is the precursor to the Gauss law, because until we are not able to understand the lines of force, Gauss law we cannot learn. So once we understand this part, the Gauss law will be pretty much easy. In fact, half of the Gauss law we can finish with this concept, and for half we have to use the Gauss law as it is given or written in textbook. So first of all, what is electric field lines? Why we are studying right now? What is the application? So first of all, it's a imaginary lines. These are not real. These are hypothetically someone's imagination. And the idea was first of all introduced by a great physicist and mathematician Sir William Gilbert. So Sir William Gilbert introduced the concept of magnetic field lines, and taking the inspiration from the same, the birth of electric field lines also took place. So these are hypothetical, imaginary, graphical representation. These are not lines. You can say lines are basically graph, and these graphs are some pictorial manifestation of the electrostatic behavior. So in short, what we are trying to do with this graph, that we are trying to explain to the world that how the charge with another charge would have interacted. Okay. And to give a visual presentation to the interaction part, this was actually designed, and it helped in various ideas to perform mathematically. So let me put some definition before we use it. These are imaginary lines. Okay. I'll just put as a point. What it represents? So it represents a graph of the resultant electric field in space. So these are graphs used to represent the resultant electric field in space. Now, why resultant field? Because imagine if you in your room you have multiple bulbs or tube light. If you switch on multiple bulb or tube lights, you cannot say that the overall light intensity distribution, who is contributing what. You cannot see the individual intensity coming from one particular bulb. What you see is the net brightness in the room. Okay. So can we define the brightness in the room of a particular bulb? If all are working together,
No.
definitely we cannot say. So similarly, electric field lines, when we represent graphically, we cannot represent for the individual lines. We only represent for the net field, like the resultant field. In magnetism, this can be achieved easily using the compass. So what we do is we take tiny needles of magnet, and these needles are, you can say, simply put on a surface, and based on the localized field at a point on the surface, the magnetic needle will align itself because of something called torque, because these needles experiences force and torque, and the alignment of the magnetic compass. If you have multiple compass, let's say you have thousands of compass, if you put, you can see there is a pattern among all these needles, and these shapes are called the magnetic field lines. So similar to the idea of magnetic field lines, which can be demonstrated easily It is slightly difficult to demonstrate the idea of electric field lines, because then we need something which can get easily affected by the electric field lines. So mostly in chemical compounds, the electric field lines are seen by the electron cloud density. They understand how it looks like, and perhaps using those ideas, they are able to create some model of the molecule. Okay. So these are graphs used to represent the resultant electric field in space. What are the other uses of this? It you can say electric field lines give the visual description of electrostatic phenomena. So the purpose of this electric field lines is to give the visual description of electrostatic phenomena. Okay. What else? So as I said, it's imaginary. So every concept which is imaginary, we have to have some sort of assumption to begin with. So we have two separate assumptions that we begin with, and from that assumption we try to create other things. Okay. So what are the assumptions? I'll write as separate properties of electric field lines. So what I'll do, I'll just end this part here, and then we'll put a heading. So there are two assumptions. First is due to isolated point like positive charge, due to isolated point like positive charge, the electric field lines or simply field lines emanates radially outward. And the second is due to isolated point like negative charge, the electric field lines terminate radially inward. So these are two prime assumptions, and there are some maybe some sub assumptions and all. So with the help of these two prime assumptions, we try to recreate the entire uh, graph, and the graphs are basically a closed nature of the interaction. It's not the absolute way to represent, not the exact way to represent. It's something called a crude way to represent, somewhat good enough to understand. So the first two things are the very important thing. If we have a positive point charge, but that is not sufficient, it should be isolated. It means we believe that there is no other charge in the universe except that charge. So if we have a positive charge which is perfectly isolated from any other charge in the universe, then the lines of force that will appear will be coming out of this positive charge in the radial direction. And you can imagine these lines as the co-initial vectors, as you study in vector chapter, co-initial vectors.
Yes.
And also these are not two dimensions, to remember, these are three dimensions. But I cannot show you the three dimensions, as you can understand. So it is spherically coming, not circularly. It's not circle, it's a sphere. Okay. So it is coming out of this center in the spherical manner. Maybe I can do something, but it will not look nice. You can understand it's very difficult to create the three-dimensional view. But you can imagine you have a rubber ball in which you have put a lot of pin or needle from all sides. So this is it's a three-dimensional, like not two-dimensional. But everything that we are going to plot on a paper, uh, we will confine ourselves to the two-dimensional idea. Keep in mind it's a three-dimensional, it's not two-dimensional. So for a positive point like charge, the lines of force will emanate radially outward. This is like a hindrance. Now the other assumption is similarly, if you have the isolated negative charge, what will happen? So if you have a isolated point like negative charge, then all lines of force will terminate radially outward. It will end here. So with negative charge, it is like a sink, and positive charge is like a source. And the domain of lines of force is between the sink and the source. So for every charge, if there is a, if the let's say if the positive is a source, so these lines of force here, these lines of force are emanating from here. So this is source. For every source, there must be sink. So even for isolated charge, we assume that infinity is the sink, which means eventually all these lines of force will terminate at infinity. So a hypothetical negative charge is present there, and that is acting as a sink, and all lines of force will go there and will terminate. And if you have only negative charge, then infinity will act as a source. And from that source, the lines of force will terminate at the given charge. So this is the idea of the source and sink. And that gives the property that the moment we have the positive and negative charge, so the moment we bring the source and sink in the vicinity of each other, then many lines of force coming from the source will end up at the sink. And the source and sink relation depends on the magnitude of charge. So two charges which are not equal will not having the complete termination or complete emanation. Only if they are equal and opposite in magnitude also, then we say that there is a 100% termination. So whatever lines of force will emerge from the positive will or must terminate on the negative. So the source and sink follow some sort of relation. So it is like if we have a charge that's a 1 coulomb. So to terminate 1 coulomb charge, we need a minus 1 coulomb charge. So to terminate 2 coulomb, we need minus 2 coulomb. Imagine if we have 2 coulomb charge which is positive and 1 coulomb which is negative, then the lines of force from the two will not terminate completely. Some will leave the negative as well and will go to infinity, because for every charge there is source and sink available at infinity. So with this idea or with this assumption, we can begin the drawing of lines of force for a variety of situation. So these are the assumptions only for the isolated case, like when we have only positive and only negative. So let's bring the case. What happens if plus and minus will come closer? So how many lines of force are coming out of any charge? Any guess? Can we count it?
Is it infinite?
Yeah, it is always infinite. I mean, we cannot count it. It's a hypothetical idea, so it's like we believe that it's infinite. But it is not perfectly infinite in a way that we can compare for two charges. So every charge will have infinite lines of force either emanating or terminating. But there is a method to compare which charge will have more and which will have less. And so it has come to the conclusion that any charge will emanate or terminate electric field lines in proportion to their magnitude. Okay. So there is a term called relative number density. Like you cannot find the absolute, but you can find the relative number density. And what we say that the relative number density of field lines is proportional to magnitude of charge. So what exactly is this? Imagine uh, two-person. One is having the thick air, other is having the, you can say, rarefied air. Someone who is bald, almost bald, or next to bald. So in any case, you cannot count the number of hair strand on anyone's head, but at least you can say that this is denser and this is less denser and so on. So there is something which we don't measure, but we can compare. So similarly, every charge will create infinite, but you may have the thicker infinity and you may have the thinner infinity. You can just think that way. So the relative number density of field lines is proportional to magnitude of charge, and mathematically, now this is most important, but mathematically, we say the number of relative field lines, I can simply density is equals to charge divided by epsilon naught, which simply means a charge Q is capable of emanating these many field lines in the radially outward direction. So you can imagine this is as some sort of number, and this number is like the number of arrows coming out of a charge. So this is only for meant for comparison, and of course not for counting. Don't get into the counting mode. Count is only the idea. So two charges, let's say if you want to know that how many lines of force one is emanating compared to the other, then this is the formula for that purpose. And we believe that Q upon epsilon naught is the number of field lines coming out of any point charge or any charge of value Q, not point charge. So if we have a charge Q of any shape, whether it's point or distributed, doesn't matter. A charge Q can create these many lines of force numerically equals to Q upon epsilon naught. And how these lines comes out of a point charge, we say readily. If the charge is distributed, it will have a very complex nature of the field, which we cannot say right now. It depends on the context. Okay, so this is another assumption that we need to be very, very careful about. So every charge is able to emanate these many lines of force. You might have seen the movie Avatar, in which you have seen that they connect to the Eva using their hair strand, right? And Eva connects to the root of the, when Eva through its root connects to the hair strand, and Eva is like the database of the entire community. And if you want some past history, you can get it back. So it's like a perfect neural system, and they can drain the DNA information using the hair strand, and all information is stored in the huge database like Eva. Very nice concept of information storing and distribution, and also the optic fiber connection of any. So now, if I have a positive and negative charge both kept in the vicinity, let's begin the drawing. How it will look like? So the beginning will be radial for sure, always, no matter what is the distribution. If we have a point charge, the beginning is going to be radial. Only after moving slightly away from the charge, the bending occurs. So the lines of force which will emerge this direction will exactly terminate at the sink. Let me draw a small space around this charge. So every charge which will emerge from here will remain spherically radial up to a small distance. For the obvious reason, the influence of the other charge cannot be experienced up to this. But the moment you move forward, it will start bending, and eventually it will terminate at the sink, the negative charge. So it will start radially and then it will sink. And it's done. I mean, you never come back. So that is also the reason we say that electric field lines are of terminating behavior. They begin and they terminate, they don't circulate. And that is the biggest difference from the magnetic field lines and electric field lines. In magnetic field lines, the magnetic field lines never terminate, they circulate. So there is no beginning or end in case of magnetism. In case of electrostatics, we have beginning and we have end. So if someone is drawing the lines of force like this, you can clearly say this is not electrostatic field, because in electrostatic field we cannot have the circulation of field lines. We must have the origin and the source and destination. So the source and sink must be clearly visible. If it is not visible, if you think it's a loop shape, you can clearly say it's not electric field lines. Okay. Of course, there are some exceptions which I will talk about later, not to confuse you. So now the second thing is the closing, the density, the packaging. If I pack these lines, or if I draw these lines close to each other, I'm trying to demonstrate a stronger intensity. So as you go away, the separation of the field lines will grow in value. Because farther the field lines, weaker the electric field intensity, or you can say weaker the field. So the separation is a way to convey the message that this is too far. And again, this is terminating eventually. The one which will leave like this will terminate like this. Like it will leave from here and will, after traveling in infinite distance, will come eventually. This is the way of writing. And then someone living here will travel some distance which I'm not showing, and eventually come here. Someone living here will travel and will come here. So what we are drawing is half is like the incompleteness because we cannot draw all, right? So this is something like kind of representation of the field lines. And you can see if you count the number of field lines leaving the plus charge, and if you count the field lines arriving at the minus charge, if the counts are equal, you can say that they have equal magnitude. So in this graph, can you see that the lines of force leaving and terminating are equal? You can count. These are graph actually, and we only draw the relative number. We cannot draw infinite lines. We just draw few lines. So this is only meant for comparison. So you can clearly see how many are leaving. Can you count? How many field lines are leaving?
Sir, 10.
And how many are
Yeah, 10 are
terminating? So because
10 are
the number which I am representing are equal for both sides, that means we can end up saying that these charges are equal in magnitude. Now we cannot say how much magnitude because we cannot count the lines. We can only say they are equal. We cannot say equal to what. Is this clear?
Yes.
Yes.
The second concept is the tangent which we draw. So these are lines of force which is representing the electric field direction at every point of space. Like let's say if you want to know the direction of electric field at this point. Yeah, for this case we can say it must be symmetric. Why? Because the magnitude is equal. So the way they emanate and the way they terminate must have the symmetricity. Only if the charges are unequal in value, the symmetricity is lost. So we'll come to that also very soon. So here, let's say if you want to know what is the electric field direction at point P. So if I know somehow what is the lines of force passing through the point P, because we have drawn few, but we can have infinite, right? So it is quite possible that we may have one from passing here also, which I haven't drawn maybe. So now the tangent drawn to the point, to the lines of force at the point P actually gives the direction of electric field at that point. So in a way, all the lines of force are representing that these are like a collection of tangents. Okay, so how we write it? It's very famous. So we can say that the tangent to the field lines drawn in the direction of flow of line gives the direction of electric field at that point. So in a space at one point, how many electric field we can have direction wise? So every point must have the unique direction, isn't it?
Yes.
Yes.
We cannot say that at one point we can have two direction or three direction. Resultant field is unique. And what I said in the very beginning that lines of force only are graphical representation meant for the resultant field, not for individual field. Okay. Individually, we know the answer, radially outward and inward. But the moment they come close to each other, they are not isolated. Now they are connected. And so the moment you have the source and sink, the lines of force will have a different flow. Okay. So the tangent to the field lines drawn in the direction of flow of line gives the direction of electric field at that point. That's too much verbose. It's common sense. The tangent to the field lines gives you the direction of it. That's it. So that comes to the conclusion that the two lines of force cannot intersect each other. Okay. So now we can say that two lines of force cannot intersect each other. Okay. Two lines of force cannot intersect each other. Why? Why they cannot intersect?
Because each
That-
line has unique direction of electrical.
Because an intersection leads to the ambiguity of tangent.
Ah, yes.
So the moment you say there is an intersection, at a point of intersection, we can draw tangent either like this or like this.
Yes. We will get two.
Now, which means at one point there are two possible direction of field, which is physically absurd or implausible. I mean, it's
Yes.
not possible. So that is why we cannot have two field direction at one point. Every distribution of charge, no matter whether it is due to two charge or 2000 charge, any distribution of charge can create only one unique field pattern. So there is no two field pattern which can be created by one type of distribution. So in space, the field pattern, one field pattern belongs to one distribution, and every other distribution will have their unique sorry, every distribution will have their unique pattern, and that is called a uniqueness theorem in electrostatics. So there is something called which means we cannot have two separate field pattern with one single distribution, or you can say we cannot create the same field pattern with two separate distribution. Okay. So you may create a same electric field with two different distribution at one particular point, but not in a space. So it may match at one point or other point, but it will not match for certain for every point of the space. Okay. So anyway, that is not part of our syllabus. It's good to know there is something called uniqueness theorem. So the lines of force cannot intersect each other. Now the question is, you might have heard about the repulsion of like charge and attraction of unlike charges. Okay. So the next point is, why two like charges repel each other? So why two like charges repel each other? The answer is simple. Every charge, if it is like, they cannot they cannot they will try to create the field lines in the radial direction. Just for the time being, assume both are equal. So if both are equal in strength, then at the plane which is the bisected, or you can say divides the two region, all lines of force from the left side will bend like this. Because they cannot intersect, they have to bend only. Because they cannot go forward, right? Can they go forward? To go forward, they need to repel each other. No? So we say that the lines of force will push themselves laterally, which results into the separation of charges. So what exactly is happening? The lines of force is trying to move forward, but because they cannot intersect it, they push themselves laterally to make a space for themselves. Now, as a result of the push of the lines of force, the charge will separate, and that's result in the repulsion. Okay. Do you realize what I'm saying here?
Yes, sir.
You can imagine that these are two blower. Okay, and both are blowing in front of each other. So air neither can go right or nor can go left. So in the middle, the air will just move, maybe vertically upward or downward, or parallel to the plane. Understood?
Yes.
So what is really repelling is this is called the lateral push of lines of force. So it's like that the lines of force are pushing each other, and that is resulting to the separation, or the charges are going away. So this is the how we explain the repulsion using the lines of force concept. So I will put it here. What I can say is, due to the lateral push of lines of force, charges gets repelled. So repulsion is, this is how we can explain. They cannot intersect, so there's no choice. They have to repel each other, and that will result into the repulsion of charges. Next point is what? So why they attract if they're unlike? So why unlike charges attract? Any guess?
Lines will get pulled towards each other.
So that's very interesting phenomenon, and let me explain it. You can imagine the lines of force as the stretched membrane or string or rubber band. So the moment they terminate from plus to minus, so it is a natural tendency of the lines of force to shrink itself. So once they terminate, they try to minimize the length. In a way, you can think like they are desperate to reach the sink from the source in the shortest possible time. So the moment they get a connection, the root, they try to shrink itself to bring them closer. Because they are very happy that if the source is and the sink is next to each other. So what we say that this is called the longitudinal contraction of the lines of force. Charge gets attracted. These are some terminology that we use due to longitudinal contraction of field lines. Unlike charges attract each other. These are explanations, okay, not the reality. I mean, I don't know how exactly it is happening, but there is a way of explaining something. And lines of force is one way to explain something. At a very advanced level, we have something called photon concept, in which every charge emits a photon called the field photon. Just like light is a photon, and light is also carrier of electric and magnetic field. So every field is a photon, and this photon carries momentum and energy both. And due to the exchange of photon, they exert force. Okay. Now, that's a whole different world of physics, and we are not going to delve deeper into that. So electric field are like light, and every source or every charge, when they emanate the field or create the field travels at a speed of light. So technically, if the two charges are light years away, even if you keep them in front of each other light years away, they will only attract after those many years, because the lines of force will reach from the source to the sink. Okay. Now, if both are positive, then technically they should interact more readily, because both will travel and they might meet sooner in between. So every interaction follows the speed of light concept. Like the interaction also travels at a speed of light. Now, in the real life, or let's say if we are performing any experiment on Earth, the separation is too small for the light, and therefore the interaction is instantaneous. It happens the moment you think of. Anyway, so that's a definition. The longitudinal contraction of field lines. Field lines. Oh, I missed something. Comma. Unlike charges attract each other. Okay. So far I have drawn the diagrams using the equal charges, right? So we'll do one more question. And these are rough estimates. Don't take it seriously. So in the JEE, what they will ask you that identify the among the following graph, identify the correct one. So they will make the three technically wrong, which means it will follow something wrong principle. So eliminating in the JEE is quite easy. But if you ask me that can we exactly draw the lines of force, it's very difficult. We do have some simulation which I can show you, but it's again inaccurate. So you can go to FET Colorado and you can see those simulations. Very poor simulation. Even the scientists have designed the simulation very poorly. You can imagine it's really difficult to implement and make it possible to observe. Okay. So right now we have three charges. Assume all are equal. So can we do the rough diagram of the lines of force? How it look like? You have to follow the rules that they cannot intersect. If it is positive and positive, they must repel. So using those ideas, can you draw the rough estimate, and then you can match when I will draw. You should match roughly. That's it.
Sir, can you draw them?
Yes. So I hope you all have drawn on your own. Okay. Yeah. So now the center is the point at which we know that no field should exist, right? Because center is, if you think of individual charge one by one, all will get field like this, and like this, and these three, four field which are equal in value and at 122 each other will create the net field 0, right? Isn't it?
Yeah.
If I extend this line and this line and this line, at this point, what do you think? The electric field should exist or not? These two will cancel the field of each other, but this will create the field like this. Correct?
Yes.
Yes.
So if you really want to draw the electric field lines, the first thing that you need to learn is, before you draw, can you kind of analyze the electric field before you try to draw? So you need to think that where the field can exist and cannot exist. And then once you have done this, you can draw the next part easily. So it will look like this. Something like this. And again, it's not accurate. It's very closely burned, bending. So I'm just making it smoother graph. Too much good graph is not possible. And also they should not intersect, right?
Yes.
So it is something like this. So if your diagram is something like this, it's correct.
Yes, sir.
Again, this was the JEE advanced problem, long time back. Now in JEE mains or advanced, you may expect one question only from the drawing of the lines. And there it will be much easier because you're not supposed to draw, you're supposed to eliminate which one is wrong, which one is right or correct. Now, they may ask you something called how many null points are present in case of a triangle. So how many null points are present in previous exam? It's very difficult part. So JEE has not considered, this is only for Olympia kind of thing. So null point means how many points you may get 0 electric field if all charges are equal. And the answer is there are 4. So one is common and the other will be on these lines somewhere here. These are the null points. Because the one is coinciding. So every line will have 2 null points. So how to prove that? There's a method to prove. If you draw the electric field of just 2 charges, not the 3 altogether. So these 2, and I hope you remember that the field here is 0 and the field at infinity is 0. So if you remember, the electric field was going increasing, and it was like becoming asymptotic like this,
R by 2.
d by 2 root 2, right? If you remember.
Yes.
So if it is d by 2 and d by 2, the answer which we got was d by 2 root 2. Okay. Now, if we have a charge here, the third charge, okay, I should have done here. So it will create its own field, which is infinitely large near it, and the field is like infinite because near the charge the field becomes infinite. But as you go away, it will decrease. So it's somewhere. So this is the point of intersection of these 2 points, and therefore every line will have 2 null points. One will coincide with the centroid, which is different. That's why I have shown it something like this. Or it will be in the opposite. Maybe it will be here actually. So the null point will be here or something on these lines. Let me remove this part. So what I have shown here is like 2 separate field lines, one due to the pair of charge, another due to the single charge. And the graph will intersect at 2 postal points. It is found experimentally, and therefore there are 4 null points available in a circle, in a triangle. Just remember this answer. So there are 4 null points. So this was asked in some Olympiad examination. Okay, now I was talking about a situation when charges are not equal in magnitude. So let's say one is positively charged and other is negatively charged. But they are different in magnitude. Let's say this is much bigger, this is very small. So now differently, the plus will have the bigger dominance than the minus. And the lines of force will look somewhere, something like this. It will go much farther and it will have the much more bending near the charge like this. So it's so much powerful that the bending will occur closer to the sink because the field is very strong of the plus. So it will try to keep it radial as much as possible. And then you can draw multiple lines. Hmm. So of course I cannot draw perfectly, as you can understand why. Now because they are not equally in value, so The sink and source can only terminate as per their strength. It is like they have 1:1 relation. Okay. So one lines of force leaving the plus will consume the one hole in the sink. You can think that. So because the negative charge is smaller in magnitude, so it will have lesser termination, but the emanation will be too much, or you can say more than termination. So let's say I'm terminating this many. Now anything beyond that will not terminate, will try to go to infinity. It looks like a jellyfish. Eh? And now you can count the lines of force leaving the plus and the ending at minus. Can you count? Am I audible, guys?
Yes, sir.
So how many lines of force are leaving the plus charge?
10.
It is,
No,
okay,
no,
it is
11.
11.
11.
No, 11.
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. One is here also, no?
Ah, okay.
Acha, acha.
The direct, I mean, is arrow. So 12 is leaving. How many are terminating at minus? Graphically,
10.
how many?
Oh,
How many are terminating at minus charge?
So 5.
Count again.
6.
It is 6.
6.
1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Can you see? 6. So now if 12 is leaving the plus and 6 is terminating the minus, it means the ratio must be 2:2.
Yeah.
So they will ask you the ratio of charge looking at the graph. And because the ratio is clear to us, and these are unequal charges, plus and minus, so where the null field can be found? The null means zero field. So on which side the null will be found? Between the charge, left of plus, right of minus?
So right of minus.
Right of minus. Why right of minus? Because the zero must be near the smaller charge, right?
Yes.
The nearer the poorer, right? If you remember the,
This we did
Yes,
in
sir.
equilibrium.
we have done this in equilibrium.
Equilibrium form.
So the field will be zero near the -2 on the right of -2, right?
Yes.
So we can say a null point will be found on the right of -2. Again, this was JEE question, advanced.
So the field line on the right side of the negative charge, where's that coming from?
Infinity. It is coming from infinity. So this will go at almost zero angle. It will make a huge turn, a radius as good as infinite, and will come back. You can imagine it's turning at tending to zero angle. So how big the ring will be? Can you imagine?
Yeah, sir. I mean, I can't imagine, but I can.
Yeah, I mean, you can imagine theoretically, not. So it is not exactly living like this. It is living at some angle, but I cannot show the angle. So it is like angle close to zero with respect to the axis. Then it will eventually turn. Okay. So let's say you are in a big field, and if you move one step and turn by, let's say, 0.01 degree, then how much time it will take to turn left? Or like how many steps you will travel before you turn left? It's like infinite steps. If I make the angle in infinitesimally zero, right? Or small. Okay. So a null point. Any doubt? Will be obtained on the right of okay. To draw it a better, you as you go away from the axis of the charge or axis line joining the charge, you must make the separation bigger and bigger. So these are not accurate diagram. So okay. So we have seen the unequal charges as well. So now the next concept is really important, and that is called the conductors. Okay. Let me see if I have left something. Okay. So now what we can do is, before I move forward, I'll teach you a new concept which will facilitate a variety of problems going forward. This is called concept of solid angle. Now to demonstrate the solid angle, we use a symbol capital omega, which you know it's ohm symbol, right, in current chapter. It is
Yes.
actually called omicron, or it's a capital of uppercase of omega. This is small omega. This is capital omega, upper and lower case. Okay. So what is solid angle and how we try it? I mean, how we realize it? So it's the angle suspended by the some plane surface, some plane you can say, a surface you can say. So an arc subtends something called angle in a plane, right? And we represent by theta. So if an arc, which may be a line also, a line is also curved. So any line and any point subtends something called angle, and we call such angle as angle in a plane. So if I move to the 3 dimension, so imagine there is a photo frame in your room. So this is the photo frame in your room. So do you have photo frame right now in your room? Anything hanging on the wall?
Yes.
Everyone?
Yes,
Okay.
sir.
So are you looking at it?
Yeah.
Yeah.
Now take your thumb and move your thumb closer to your eye, close enough to hide the frame. It should be invisible, like the thumb should be obstructing the entire view. So you need to bring somewhat closer, right?
Yeah.
You can see now the view is hidden, right? The thumb is obstructing the entire view, right? Now you cannot see.
Yes.
So what is happening? The light ray from every point of the surface is arriving at the eye. And not only 4 points, I'm just taking some point, but it is coming from every side, like every point you can think of, it's coming from every point in this. And what your thumb is doing, it is coming in path. So why you're not able to see the frame using the thumb, although thumb is smaller in size, because your thumb is subtending exactly the same solid angle as the frame on your eye. So this solid angle, of course, you cannot see it. You can just understand the idea. It's a three-dimensional angle. So this angle we call omega. And you can see it's three-dimensional. Like it's coming from all directions, like some sort of, if it is a circular base, you can think this is a conical angle. It's like a tetrahedral angle. Right? It could be any angle. So the solid angle is the angle that is surface. Sorry. So solid angle is the the angle suspended by the subtended by what I'm suspended. I'm saying. Angle subtended by the surface on at a point. Okay. So your eye is acting as a point, and these frames are subtending some angle at the point, and that angle we are seeing as solid angle. Now, how to measure it? So of course, the angle measured will depend on not only area but also the separation from the point. You can see a smaller area closer to the eye is capable of subtending the same angle as the bigger area farther from the eye, isn't it? Now the concept of sun angle is so powerful that you can completely hide the sun using your thumb. You can imagine how big is the sun, but still the light ray is coming, is creating a solid angle on your retina or on your eye, and through that angle that is visible to you. Okay, through that angle. So the solid angle is the angle subtended by some surface. Okay. Now to measure it, we have to go back to the theory of plane angle, and we'll try to draw some analogy. So the definition of plane angle comes from the circle. So in a circle, we have something called radius. And we have something called arc length. So this arc length and this radius is subtending some angle at the center, and this is called angle or in a plane, which we express in radian. So this angle in radian having a definition, and what is the definition? Arc length
Radius.
by radius, and clearly this is the ratio of length upon length, so it is dimensionless quantity, as we know. But the ratio of two number will give you another number, so this is always a number. So theta is a number actually. 1, 2, minus 1 is like 1, 2, 1, 3, something like that. So the L upon R is the definition of plane angle in radian. So we can draw parallel from 2 dimension to 3 dimension. So in a 3 dimension, what is the analogous of circle? What is the analogous of circle in 3 dimension? Hello guys, am I audible?
Yes, sir.
So what is the analogous of
Me, I
circle in
didn't
3
get the
dimension?
question.
What is the analogous of circle in 3 dimension?
Sphere.
A sphere. So on any sphere, at the center of the sphere, if I choose any patch, so patch is like a small area. Let's say I choose the patch. Now this patch lies on the sphere. So if you join the patch to the center of a sphere, okay, then this will also subtend some solid angle. So if I choose the area as a small value dA, the R is same for every point on the patch because it's part of a sphere. Then the d omega that this patch will subtend at the center will be the ratio of area upon what?
Radius.
Square. Why? Dimensionally, it should be dimensionless, right?
Yes. Yes, yes.
That is the, you can say, correlation that we can withdraw easily from going from circle to sphere. So this is the only formula that we have. Any other formula, if you want, we have to derive using this formula. So given a spherical surface and taking a part of it, we can find the solid angle that surface must be subtending at O. So if I take the entire surface, what is the total area? So the entire sphere will subtend how much area at O? What is the, sorry, what is the total area of the sphere? Surface area?
4 pi square.
So what is the total solid angle?
4 pi.
4 pi. That is called the, but the solid angle, how we measure? In sphere area. Now for you, it doesn't matter how you measure. You can just name it a radian, sphere radian, but the SI unit of solid angle is sphere radian. So the entire sphere at the center will subtend, not center, at any point, in fact, inside will always subtend 4 pi sphere radian. In a circle, what is the total angle subtended at center? Tell me guys. What is the total angle subtended at the center of a circle by the entire periphery? Yes,
360.
in radian,
Oh,
2 pi. 360 is called the division, the angle expressed in division. But when I say how to measure and how we measure in radian, because the radian represents a number. And 360 is not a number, it's a division. Okay. I hope this is clear.
Yes.
So there are 2 points which you need to remember, that at any point in a sphere, or not only sphere, if you take any closed surface, so if you take any closed surface inside the sphere, the solid angle subtended will be always 4 pi. If the point belongs to the inside the volume, and if it is any closed surface, the net solid angle will be 4 pi sphere radian. I hope this is clear. And
Yes.
it doesn't matter. Imagine if I draw a closed surface around this sphere of random shape. So if I take O point, what is the angle subtended at the point O by the entire random surface, the red one? It is still 4 pi, no? Not getting it. So this will subtend, this area will subtend same as this area.
Yes.
Yeah.
If I consider all such area, so eventually it will subtend same as the sphere, no? So the shape doesn't matter. As long as it is closed and as long as it is inside, the total solid angle is bound to be 4 pi. So you can put a note because you guys are not getting it. Let me put a note. So what we can write? The total solid angle at any interior point of closed surface is 4 pi sphere radian. So the radian and stereoradian you study in class 9th as a supplementary units. So we have 7 SI unit and 2 supplementary units, right? Angle of plane and angle of 3D. So there you only study the name. Now you are using it for the first time. So in the 3 dimension, this is the how we represent. Now the question is, what if the surface is not part of a sphere? Then how we can do it? So imagine we have a surface, maybe in form of a disk. So let me do one surface. So let's say we have a surface like this. And we have a point over here. And now we are trying to understand what is the angle subtended by this random surface at O point. Now clearly this is the angle, let's call it d omega. But we don't have formula for a surface which are not like a sphere. So this is the area which is small patch, but it is not part of any sphere. So I cannot have form. But this is at a distance r away from the O. Okay. So how we can get the answer? Any idea? So the trick is simple. We draw a sphere of radius r. So first of all, I'll draw a radius from O to the center of the patch. And do remember, this is a small area. dA means nothing. You cannot see it. I am drawing something like this for illustration. So imagine the sphere of radius r. Okay, is it looking fine? The sphere of radius r.
Yes.
So there must be some equivalent patch, or you can say the projection. I can say if I extend this line, if I extend this line under this, so this area, which in color, so you can see there is a small projection of this area over this sphere. How to show? How to show? Okay. So the pink region is actually representing what? The area on the sphere subtending same angle as that the actual surface given to us. Are you getting this point? Now, every surface area will have area vector. How we represent the area vector? By drawing the line normal to the surface. And the radius vector will have the radial direction. And this is the r cap. This is the dA vector. And we define the angle theta. So we are looking for the projection of this area onto the sphere. Like what is the equivalent area that this area will have on the sphere? Can you guess the equivalent area onto the sphere? Maybe not. So let's take the area projection. So imagine the slant area. I'm calling the slant area as A. What is the base area? Imagine this is theta angle. If I call this as length as L and width as B, the area is L into B. So what is the area of the base, which is like a projection or shadow on the plane?
L cos.
So the projection will be L cos theta into B, correct? Yes or no? Tell me, guys. Is this clear? Yes or no?
Ah, yeah.
So we can see A projection, the projected area is how much? It is like A cos theta. Now, what do you mean by area vector? I hope you remember the area vector. Area vector is always a vector which is perpendicular to the surface, right? We don't remember it. Okay. The area of the base is A cos theta. So area vector, how we define? We define area vector always by drawing a perpendicular. Vector is always the, so area vector we always draw perpendicular. This is A vector. And if you tilt, you can see the the projection. If I draw a vertical line, this is the area vector of the bottom, correct?
Yes.
Area vector of the bottom surface will be like this. And fortunately, this theta will also become the theta here. Okay. So the A projection will be A cos theta. So this is the bigger one. So the way we resolve vector, we can think that way also. So if dA is the area of the surface, what is the dA of this surface, the pink one? The dA dash. Let's call it dA dash. So dA dash can directly write as a projection, which is dA
dA cos theta.
cos theta. So if we know the area vector, because this is also the area vector of the dA dash. So the component, because dA is given to us and we're looking for dA, which is the projection of dA, we're looking for dA dash. dA is given. So dA dash will be dA cos theta. But the moment you get dA dash, it is part of the sphere. And we know the answer for solid angle in terms of that. So what is d omega? dA dash by r square, if you remember.
Yeah.
And therefore this turns into a formula dA cos theta, the actual area of the surface upon r square. And for curved surface, area vector is only defined if it is elementary. Because you can only draw normal to the flat surface uniquely. So if surface is flat, then every normal drawn will be similar. But if surface is curved, if surface is curved, then normal at every point will change the direction, isn't it?
Yes.
So our large curved surface cannot have a unique normal. So that is the reason whenever the surface is curved, we take elementary patch so that it can have the well-defined normal. Okay. So the moment you have any elementary area, you can define the d omega. Okay. And the formula we derive from the sphere only. But if it is a non-spherical surface, you have to convert somehow into a sphere. And then using that answer, you can derive the answer. So we have anyway derived the answer, and you're only supposed to use it as and when required. So the d omega for any surface is this dA cos theta by r square. Now, what is theta is important. Theta is the angle between r vector and the actual area vector. In sphere, theta is always 0. Understood? So in sphere,
Yes.
theta is always 0. And that is why the d omega always turns out to be dA by r square. So the moment you take a spherical patch, the radius vector and the area vector will be parallel to each other. That's the only difference that you need to remember. Now we are really interested in calculating the solid angle in terms of some variable. Let's see what kind of variable I'm talking about. Like an eyeball, right? So imagine this is the patch. Now, if you join the center to this beginning and the end, this is the radius, of course, r. This is theta. This is not theta. I use for the plane angle. Okay, so this is I'm drawing for one particular plane. Taking this elementary ring which I have cut. Now, if you draw the on both sides, then this angle this is the angle called the solid angle subtended by this area, okay, which is at angle theta. This angle, the shaded portion is subtending d omega. Just like the theta and d theta, the angle, the solid angle between theta and theta plus d theta, which is like the solid angle only for that part. So now this radius will be how much? What is this radius?
Sine theta.
This radius will be r sin theta.
Yeah.
Okay. So the question is how to find the d omega. See, no matter what shape the patch is, if the patch is part of a sphere, you can always write d omega as dA by r square.
Yes.
And r is going to be same for every patch, no matter which patch you choose. Now the question is how to write dA. So this width is r d theta,
Yeah.
and the circumference is 2 pi r sin theta. So area, how we write? 2 pi r sin theta into.
RDQ.
See, so far I have been doing this horizontally. Today I am doing vertical. That's why the confusion is there, right? So we have done this. We have done already, right? These are the examples.
Yes, sir.
Just in case, if, yeah, this is the same thing. So the solid angle is like this, something like this. I'm just doing it here. So d omega is defined as this upon r square. You can see r square will cancel out. And you're left with 2 pi sine theta d theta. So I'm particularly interested in that if I move from 0 to theta, like if I capture the entire surface of the sphere up to theta plane angle, then how much solid angle that will subtend. So I want to know T omega as a function of theta. So definitely I can integrate d omega. And this will become 2 pi sine theta d theta, and I want to integrate from 0 to theta. Okay. So 0 means you are here at the tip of the, and as you go away, it will cover the. So let me do a separate part. So what I'm trying to say that if I consider the entire patch, if you consider the entire patch up to theta angle, then what is the solid angle subtended by this entire? Is omega. And now this is easy. You can just integrate this one. And this turns out to be 1 minus cos.
Yes.
Now this formula is so famous and so useful that you are supposed to remember by heart. If you know the derivation, it's really good. If you don't know the derivation, it doesn't matter. But at any cost, you must remember this formula. So now this is derived using the sphere. But what I'm trying to say that it is not about sphere, it is about the cone actually. Any cone of semi-vertical angle theta, any cone of semi-vertical angle theta will subtend the solid angle omega, and that is written by 2 pi into 1 minus cos. Because angle is subtended at 4, not anywhere else, right? Understood? So any solid angle, any conical surface whose semi-vertical angle is theta, the total solid angle it will subtend at the vertex will be 2 pi 1 minus cos theta stereo. So it's a relationship between the plane angle versus solid angle. Is this clear?
Yes.
So for the entire sphere, the theta will vary from where to where. How to capture the entire sphere? Theta will go from 0 to pi.
Yeah.
So when you put cos theta equals to pi, when you put theta equals to pi, you get the entire sphere captured. So cos pi is minus 1, which will result into 4 pi again. Same answer, right?
Yes.
So any closed surface will subtend 4 pi, and that's the answer that we should know. Okay. Now, this is the formula that you need to remember. Based on this, we can solve variety of Gauss law questions. But that will go later on. Right now, my intention was to solve one question of lines of flows. So if we have two charge, Q1 positive and minus Q2. Q2 is negative. You can choose anyone as bigger or other as smaller. So let's choose some. Let's make some assumption. Let's say Q1 is more than Q2 in magnitude. So the lines of force per unit solid angle will be more in which case? Who will emanate more lines of force for a given solid angle?
Q1.
If I draw a sphere around Q1, and if I draw a sphere around Q2, and if I choose the same solid angle, both sides, so both will contain same number of lines of force or different number.
Different.
Okay. So how to make them equal? Okay, so we can see clearly that if I choose the same angle in both cases, this will have a relatively more number of lines of force coming from this entire solid angle compared to this, right?
Yes.
U1 is more, U1 will emanate more lines of force in a given angle, right?
Yes, sir.
Not to equate these two, like I want the same lines of force should come from Q1 and terminate on Q2. Which angle I should reduce, the left or the right?
Left.
Correct. So I should must reduce the left angle. So what I will do is a relatively smaller angle of alpha value is sufficient to create same lines of force that beta can terminate. And if you remember that in the very beginning, I had drawn the lines of force something like this for a big and small. You can see here. Yeah, this one.
Yes.
You see a small angle. You see that?
Yes.
So it means every lines of force which is part of this angle alpha is equal in value or number as this can terminate in the angle beta. So what beta can terminate is the what alpha can emanate. So how to relate alpha and beta? How we can relate? Any idea? So then we have to use the relation that a charge Q emanate Q by epsilon naught lines of force through 4 pi steradian, right? So it is emanating these many lines of force through a spherical surface, right? So the entire solid angle 4 pi will capture the entire lines of force Q by epsilon naught, right? Okay. So you can see clearly that if this is alpha, so can we say this angle is omega 1? And can we say this angle is omega 2?
Yeah.
So we know that 4 pi steradian captures these many field lines. So one will capture how much? If this is the solid angle,
Q4 pi.
and this we call phi. Later on we call flux kind of thing. So one will capture how much? Q by 4 pi epsilon naught.
Yeah.
So how much omega will capture? How much?
Omega Q by 4 pi.
Omega will capture the given answer into omega,
Yes.
right, guys?
Yes.
So knowing the solid angle gives the alternative way to understand how many lines are capturing or being captured through that entire angle. Okay. So we represent this as phi omega In some context, this is also called flux, but you can think as a count of lines of force. So in a context, the same lines of force becomes by definition flux. As of now, we'll only call phi. So the phi through the omega is equals to this value. So if I know the omega, I can find the phi. It's pretty easy. Now we know that for conical surface, the omega depends on the semi-vertical angle. If you remember,
Yes.
I hope this is clear so far.
Yes.
So the word phi we can also relate with semi-vertical angle thing, and therefore this turns out to be if you know the semi-vertical angle of a cone, you can exactly calculate how many field lines are leaving. So now knowing this formula, can we say phi 1 equals to E1 by 2 option naught into 1 minus cos alpha? Yes or no?
Yeah.
And phi 2 equals to Q2 by 2 option naught, we are writing value only 1 minus cos beta. Can we write yes or no? Can we write, guys? Tell me.
Yes, sir.
Yeah.
So, so if we have phi 1 and phi 2, our assumption was these are equal. Because we are trying to understand that for equality of lines of force, what angle will have the relation, right? So as per our assumption, the flux through the alpha angle of Q1, flux means the lines of force through the alpha angle due to Q1 will contain the same number as the angle through beta of Q2 will terminate. So once you equate these two, what you get? Okay. So you can write like this, you can solve this. So what we are left with is Q1 into so Q1 by Q2 is that is a formula for the 1 minus cos alpha.
Yeah.
So this is the relation between charge and the alpha beta. So if a lines of force is leaving at angle alpha, it will terminate at angle beta. All right. So this is from SS Kurto book, Physics for Everyone, which is nothing but the collection of Russian Olympiad questions from the late 60s to 90s, or 80s, I think, or 90s. Yeah, much before I was born. Don't. So the relationship between the lines of force and the angle is of great uses. If you look at the JEE advanced problem, most of the question can be solved with this concept of solid angle without any effort. So one particular example is again very famous. So if we have a ring and from the axis of a ring, if we have a charge q, now the lines of force from this charge will emanate in all directions. The question is how many will pass through the ring. Now it is interesting to know or understand that this is the if you draw the line from the periphery of the ring to the charge, it will form a cone actually, right?
Yes.
And therefore every lines leaving this solid angle will eventually pass through the ring because of the location, right? So whatever lines of force will start from here will eventually pass through the ring, right? And any lines of force beyond this angle will not be part of the ring, isn't it? So how many lines will cross this ring? Can you guess or tell me? What is the phi to the ring? So here the theta is not given, but you can calculate theta easily.
We know the tangent.
Pardon? So ring will be how much? Tell me. Phi ring is, yeah, tell me.
Or Q by 4 pi epsilon naught into 1 minus, yes, 1 minus cos theta. Cos theta is x upon root of x square plus r square.
So it is 1 minus x upon.
Yes.
Now later on, when the same electric field lines crossing a particular contour or area, we call it electric flux. So the same count when calculated over any surface area, we call it flux. So this is called electric flux through the ring. So flux is nothing but the count, like how many relatively lines of force will go through that region, okay, which you have put arbitrarily. Like you have just designed a region. You are saying that if I have this particular area or the region, how many lines of force I will witness coming out of it. So when the lines of force is counted through an area, the term changes, we call it flux. So flux is not something extraordinary, it is just a way of saying it. Okay. So with this, I will end today's lecture. And the other application, I'll continue the next lecture. So if you ask me what is your homework, there is no homework because we are in midway of something. You continue
To ask
your
one
AC
thing.
Verma. Continue AC Verma and solve as much as you can.
Hello.
Yes.
I wanted to ask one thing. You had told us to start seeing the chapters, like the different chapters.
Yeah, yeah.
So,
So
but
yeah, you start with the
huh.
properties of matter.
But how? But like in a week, how many videos we should aim to watch? That was my question.
You should see properties of the matter should be finished in next, let's say 1 month or
Okay.
less. So make sure that not watch every day, but you watch something at one go. Like you dedicate 1 day to watch at least 2 to 3 lectures. Okay, so that you can correlate things easily. If you watch one, then after one, you will forget the context in which the same thing was said.
Yes.
Okay, because in between you're learning so many things, so you will not keep a track of what happened in the last lecture and what is happening now. So while revising, the best way is like you watch the videos at slightly better speed. Generally, lectures are 2 to 3 hours, but the effective time is 1.5 hours maximum. So you start with the properties of matter, then come back to the elasticity. Okay. I think sorry, you have to start with the elasticity part. Elasticity, then properties of matter.
Yes.
Yeah, the sequence you will follow is elasticity first, then properties of matter. Actually, it's a part of same thing, but elasticity, then surface tension, then viscosity. These are the sequence already given in the same sequence. So watch one by one, and after watching, just finish the S1. That is sufficient.
Okay.
So when I will take the doubt class or the problem solving session, I will give you the difficult questions. Most of the questions I have discussed in the lecture itself. Mostly, if you only revise the entire lecture and entire problem of the lecture, that is sufficient for JEE Advanced. Nothing more is required.
Okay.
All right. Bye, guys. Take care.
Thank you.